Good morning, everyone. My name is Luis Castillo. Today we're going to have a webinar about design recommendations for Huawei Solar PV utility scale solution. This webinar is a recollection, let's say, of design points and considerations that we have found useful for the clients throughout the years, common questions that the clients ask. And hopefully this will answer a lot of questions that you have in terms of the product and how to use it for ground-mounted large-scale solutions. So first, I want to start with our current portfolio. For those of you that are familiar with the product, we have inverters for residential, commercial, industrial, and utility applications. Today, most of the examples and scenarios are based on the utility scale, but the architecture of all of the inverters are similar, so you could consider this also for commercial and industrial applications or residential even. So on the utility scale, we have at the moment two inverters, the 105 kTL and the 185 kTL. Main difference is the power, of course, and the input current per MPPT. But the architecture, as I said, of the inverters is the same. Then we have a transformer station, which comes in two sizes, 6 and 3 MVA. This equipment at the moment is not available in the UK, but we are going through the respective certification process, and we are aiming to have this available at the end of this year, beginning of the next. And then we have our Smart Logger 3000B, which is our last generation of data logger, and the Smart Array Control Unit, which is a cabinet that supports, that holds the Smart Logger and the AntiPID unit if required. I'm going to speak that. Sorry, I'm going to speak that about it later on the slide. So before moving forward, I want to describe some characteristics of the 185 kTL. Like all of our inverters, it is a multi-MPPT string inverter. We have 2 strings per MPPT. Some important characteristics that you want to take into consideration when you design is the maximum input voltage, which will define how many modules, well, it will be one of the variables to design how many modules per string. The maximum current per MPPT, which will define how many, or the losses, how much current can be processed by the inverter. The maximum short circuit current per MPPT, which will define how many strings you can connect where per MPPT in the case you want to push further from the default 2 strings per MPPT. I'll explain how you can do that. And the number of inputs, which, like I just said, you could increase if necessary. Important, this is a 185 kTL, but like any electronic or equipment, it is rated by temperature. So depending if you are designing in places with very high temperatures, like for example South Spain, you might want to consider a design based on 175 kilowatts, for example. And the connections, the connectors the inverter uses, it is very important that you keep in mind when you're making an installation to use a connector that is compatible with the inverter in order to avoid problems like arc fault, for example. So on the SACU box, we get a lot of questions, a lot of confusion. What's the difference between the Smart Logger and the SACU? Well, there is no difference because they are not related, basically. We have a Smart Logger and an AntiPID unit, and the SACU box, which means a Smart Array Control Unit, is just a cabinet that holds both of these equipment. Inside the SACU box, you will find a Smart Logger and the AntiPID modules. For example, you have a picture here of a SACU box open. You can see on the left panel, on the left side, and there is an AntiPID module. Next to the AntiPID module, there is a slot to use another AntiPID module, which is will be necessary in the case you have a double winding transformer. So you will need an AntiPID module per each winding. And then you have the smart logger with the protections. All of this comes within the SACU box, and you don't need to prepare any of this protection. You just need to connect the cable, and that's it. So starting with the one of the first common questions is what is the best place to locate the inverter? String inverters give you the flexibility of play a little bit with the location of the inverter. Normally with the central solution, the best place will be the center of the array. Here, depending on what are your needs, on your model, on your situation, you could have a couple of options that I will recommend. First, a distributed approach, which means that your string inverters will be scattered around the, let's say, the array. Let's take this example for a 6 MVA block. So in this case, in a distributed approach, your inverter will be in the center of, for example, 6 tables or 10 table arrays, and your string cable will go to the center of this array where the inverter is. The advantages of this let's say method is that you will reduce significantly your string DC cable. You will increase on the contrary, you will increase slightly the AC cable, but the cost benefit of decreasing that much the string should be superior. However, the main disadvantage is that you will need inter-row trenching. For some projects in some countries, this could become a bit expensive. So this is one of the trade-offs that you need to consider. The other option, I would say perhaps more popular, is to place the inverters at the end of the row, where all of the inverters will be aligned, let's say, parallel to the access row. The advantage with this is, yes, you will reduce a little bit the AC cable, but you on the contrary, you will increase a lot the DC string, which will increase the cost. But the other advantage with this is that you will not need inter-row trenching, which could be reduce the cost significantly as well. So I will recommend for your ground-mounted project to consider these two options and evaluate from mainly an economic point of view, which is the solution that best suits you for your project. In terms of the inverter, there's no difference, of course. The inverter could work in both situations. There is a third solution. Let's say some people call it a virtual central solution or a cluster array, where you put all the string inverters very close to the substation. This is I wouldn't recommend this because it's in this scenario, because it will increase too much the DC string, and this will be definitely not an increment in cost that you will want, especially in a 6 MVA block. This central solution could work if you have a couple of inverters, just a handful of inverters, so where you can put them close to the transformer station, and then you will not be affected by the increment of the DC string cable. But in principle, for large projects, I would say the distributed or the next to the row approach will be the main solutions. So do I need to protect the inverter from the sun? We get this question a lot because there is a recommendation in our user manual to put the inverter below a shed or our awning. As you can see here, as I was mentioned before, also like any electronic equipment, the inverter degrades with temperature, which means that the maximum output power of the inverter will decrease with the increment of the temperature. You can see an example curve here for our 1 and 5 KTL. Normally, if you design 30 degrees Celsius or below, the inverter will not experience any derating. But this is the main reason why we say we recommend, it's not mandatory, but it's a recommendation, to protect the inverter in order to avoid any derating during high temperature periods like summer. The easiest way to do this, and it doesn't cost anything, is to place the inverters below the module tables, and this will give you enough shading to cool down the inverter during high temperature periods. Of course, it will depend where your project is located. If it's somewhere in the Sunbelt region, like South Spain or South America, and there is nothing you can do. You will have periods where it's extreme temperatures, and the inverter might suffer some derating. In terms of inverters projects close to the sea, we get the question that if we have a solution for this. Basically, our inverter is designed for harsh environments. As long as you place the inverter 500 meters away from the coastline, this should be fine, and the inverter will not be affected. If your project demands a proximity closer than 500 meters from the coastline, I'll recommend you get in touch with us. Depending on the situation, we can find a solution discussing with the R&D team and evaluate if the project is viable. In terms of communication, so a lot of clients are interested to know what you can monitor with our smart logger or with our solution. For that, we have a document that is called the Modbus register. Our technology uses the Modbus protocol to communicate. So in this Modbus register, you will have a list of all of the parameters you can play with during your monitoring. Basically, the parameters are defined in two characteristics parameters that you can only read, like, for example, the hour, the active power, the input current parameters that you could read. And there are parameters that you can read and write. You can, for example, rewrite a power adjustment, a power derivative for the inverter. If for whatever the reason, maybe an export limitation, you need to derate the inverter from 100% to 70% output power, you can do it, and this is one of the parameters you can rewrite. If you need this document, you can get in contact with us, and we can share it. So in terms of a PPC, a power plant controller, we also get a lot of the question that if we provide this. Unfortunately, we don't. This is an equipment that is outside our scope. At the moment, we only provide inverters, transformer station, and a data logger to log all the parameters of the inverter and the transformer. Our team is also working on developing a storage solution that should be available next year. This will increase our scope in terms of technology, but as for PPC, we don't have a plan for that. So the PPC normally will be provided by your monitoring company, which most of you already have contacts with. For those of you that are not familiar with what a PPC is, will be an interface between the DNO and your site. It will be the main controller, the main brain of the site, and it will allow the DNO to, let's say, manage or control your site and give instructions like the rate or injection of reactive power. The good thing is that we already have sites that are installed with PPCs from different companies, and these companies, they already are familiar with our technology, so there is no concern on compatibility with the PPC. So you just need to get in touch with the monitoring company, and they will explain any special requirements if necessary. For communication, for those of you who are familiar with our technology, we offer two methods of communication. It will be through the conventional RS-485 cable or through MBOS technology, which is our new generation of PLC, power line communications, where the data travels through the power cable. This is advantageous, and we recommend this approach because it will reduce the capex of your project, and your communications will travel through a more, let's say, resistant cable, which will be underground. As you know, the RS-485 cable is subject to damage because it's a very thin cable. So our recommendation will be to use MBOS, but this is optional, and all of the inverters come with the capability of using both. So, but if you do decide to use MBOS, there are a couple of considerations that you need to take in mind. For example, if you use with the 185 KTL, if you use a multi-core cable, you can place the inverter up to 1,000 meters away from the LB bus bar, where the communications will be collected by the smart logger. If you are using a single core cable, we recommend that this distance doesn't exceed 400 meters in order to guarantee the quality of the communications. On the side of the smart logger, you will need to place the smart logger no further than 10 meters. And also we recommend that the cable between the smart logger and the LB bus bar is of a section of at least 10 square millimeters. We do get a lot of questions why this cable has to be so thick for such a small equipment. And the reason is that this is not mainly a power cable. This is just to guarantee the PLC comms or the MBOS comms can be transferred with a good quality. Also, if you do decide to use MBOS and you decide to use a single core cable, the recommendation is to strap together all the faces every meter or so in order to help the MBOS communications. All of these details you can also find in the user manual, so you don't need to take notes. So in terms of string sizing and DCAC ratio, we get a lot of questions about this. One of the most popular is how many modules can I connect per string? And the answer is depends, because this will be, of course, subject to the module that you are using and the location of your project and your design considerations. So the most popular way of doing this is as per the standard IEC 62548, which, as you know, you do it taking into account your open circuit voltage at standard test conditions, STC, and correcting that voltage subject to an absolute minimum temperature. That absolute minimum temperature, it's for some people it's the lowest temperature they find throughout the year or historically. However, it has found to be that this approach is too conservative, and it might not be the best solution from a techno-economic point of view. So now you have on the IEC standard from 2018, 62738, this lowest temperature could be the mean of the low temperatures, which this will, of course, increase the value of this absolute minimum temperature, and it will allow you perhaps to connect one or two extra modules per string. And if you want to even, if you have enough data, you can even refine this approach and consider only the temperatures around sunlight hours, more specifically during sunrise. In this case, as you know, you take an approach by considering not just the temperature but the irradiance, and the VOC, the open circuit voltage, a lower irradiance will be lower, which will allow you to connect more modules per string. In any case, if you have any doubts and you are concerned about if you are connecting to too many modules, you can get in touch with us. We can tell you, we can approve the design. We will tell you, yeah, we are happy. We're connecting this many modules on the inverter under these conditions. And you will have, let's say, a support from us on that side. So the advantage of connecting several modules per string is not just the from the techno-economic point of view on the savings that you can do. It's also that our inverters and our new generation of inverter, for example, they work the highest efficiency point is also at high voltages, at high DC voltages. So if you have a short string, you might be missing this efficiency point in some places. Compared to this conventional solution, the central inverters, normally this high efficiency point is more around 900, 800 volts, which will make it less efficient if you start making long string designs, like 29 or 30 modules per string, like you can do now with the current 400, 450, 480 modules. So when you do a long string design, you are not only making savings, but you will also be getting close to working at the most efficient level of the inverter with our solution. So we definitely recommend a long string design for your ground mounted project. So in terms of DCAC ratio, we do get asked this a lot. What is the maximum or the optimal DCAC ratio for your inverters? And again, the answer is it depends. The DCAC ratio is not optimal for our inverter or for a specific model. It will be optimal for your project, taking into consideration the characteristics of your project, which modules are you using, which configuration are you using, and especially the location. The optimal DCAC ratio will depend on significantly on your location, and it could change depending on this. For Huawei inverters, what you need to take into consideration is that you have a maximum current per MPPT, for example, which is 26 amps. If you exceed this by, let's say, connecting high power modules, or well, with the current module technology, you won't exceed this, but let's say you use Y connectors, which I'm going to talk a little bit more about later in the next slide, you will be perhaps exceeding these 26 amps under some circumstances, probably during summer. Nothing will happen with the inverter. What will happen is that the inverter will start the so-called clipping losses, in which if after 26 amps, the inverter cannot process, and you will start having some losses. The good news is that our inverters have the MPPT booster, and during these periods, the inverter will be capable to increase the voltage in order to reduce the current and minimize as much as possible these losses. As you can see in this table, we have done some studies, and actually the clipping losses with different DCAC ratios, and depending on the location, they are very minimal. So you shouldn't worry too much about this. When it comes to the short circuit current per MPPT, if you decide to use Y connectors, you will increase the current per MPPT. So our recommendation is to do this only one extra string per MPPT. Let's say by default, you have two extra strings per MPPT. We recommend that if you're going to use one connector, you install only one more in order to avoid getting too close to this number. As I was saying, here with the Y connectors, you can do it. And also, a very common question is if the warranty of the inverter is going to be affected. The answer is no. You can use Y connector, and this will not invalidate the warranty. The only recommendation is to keep in mind the maximum short circuit current per MPPT, and only use one extra string per MPPT. And also, you don't need to use, if you don't want Y connectors in all of the MPPT, you can also, for example, if you have 18 inputs by default, you can only add 2 extra strings in MPPT1 and MPPT2, and that's it. You don't. Also, if you use Y connectors, we recommend that you use fuses. As you know, by default, but with 2 strings, you are not required to use fuses because the reverse current of one string will be the same as the other one. But if you add one extra string, you will need to put fuses on those 3 strings in that MPPT. But the rest of the strings in other MPPTs that doesn't have a Y connector, they can remain without fuses because they are the MPPTs. They are independent from each other. So some information on PID cables. So also very common question: Do we have an AntiPID solution? The answer is yes. But before, I want to discuss a little bit on what actually AntiPID free means. Most of the modules in the market that claim that are PID free, they are based on the IEC 62804. This is a test in order to test the AntiPID, the air temperature and the humidity will be changed. But the important point here is that under this test, the module can be considered PID free if the power loss after the test is less than 5%, meaning that you could have PID free modules, but still have a 5% loss due to PID. 5% loss for a large scale product, it could be a lot of energy. So I would say you would like to avoid this. For that, we do have an AntiPID solution that we recommend you install at the beginning of your project. Basically, what our solution does is we create a virtual neutral point that is linked to the DC side of the inverter, and by increasing the voltage on the AC side, we can also shift the negative potential between the PV minus and the ground, and hence eliminating PID. So, but there are some design considerations if you do decide to use our AntiPID solution. The first one will be that, as I was saying, we increase the AC voltage on the ground side, on the neutral. So you have an example here. Under normal circumstances, this will be 800 volts, around 800 volts and 500 volts with a 10% tolerance. But if the AntiPID module is working, the line to PE voltage will increase. It will increase very close to 1,000. Normally, the cable that is used in utility scale solution is a 0.6 voltage to ground and 1.1 face-to-face voltage. We recommend, if you use our AntiPID solution, you go to the next level. Some of the manufacturers, the cable manufacturers, they have 1 to 1 kV, and also some of the manufacturers we have seen that they can confirm that their 0.6 to 1 to 1 kV can actually withstand higher voltages. If you get the confirmation, you can proceed with this cable, or simply just get the next level of insulation, which should be around 1.83 kV, or like I said, in some cases you also have a 1-to-1. That will be the first point. The second point is if you work with an AntiPID solution, the method of earthing must be an IT grid. In terms of cable, copper or aluminum, there is of course no preference on this. You can work with copper or aluminum. This will be completely a commercial solution, let's say, if you can find a good price. The inverter can work with both. The most important thing here is copper needs to be connected to the inverter terminals. So if you do use an aluminum cable, you need to make sure that you install bimetal locks in order to have copper connected to the AC terminal. There are a couple of solutions that you can do in order to install this. If you have any doubts, you can also get in contact with us and we can confirm if your solution will be appropriate. You can also refer to the user manual and we explain a couple of scenarios. For the PE, this is also a very common question. As you know, you need to install a PE for protection. The 195 KTL, you could do it in two ways. You have a PE on the inverter terminals, or you also have an external lock. You can use any of them. It's up to you. Normally, I would say, in my experience, the most common is the external solution, and it will also perhaps the most practical and the best solution, because you are connecting directly the inverter to the structure, to the module structure, which is normally must be grounded. So this will be the easiest way to do it. But you can also, for example, do it through a 4-core cable with a PE, use the PE inside the terminal, and then go to the equipotential grounding that you have on site. In terms of G99 requirements, we do have a G99 certification. At the moment, we have this for all of our portfolio in the UK. What we do is normally we go for a third-party lab. We test the requirements. We get a certification. All the capabilities on the G99 requirements are tested here. Reactive power, fault right through, frequency response like limited frequency sensitive mode, over frequency, under frequency, fast fault current injection, voltage control. The DNO will most likely ask you for this document during your compliance process. All of these reports have been uploaded to the ENA website, which can be accessed by the DNO, and they can get the information from there. For type A sites, there is the type test verification report, which you can also access on the type test register portal. This can be downloaded directly by yourself. As I was saying before, for type B, C, and D, you will need full type test reports that can be accessed directly by the DNO. In any case, if you have any questions about this or you want specific details, you can also contact us and myself especially, and we can discuss about it. And finally, for how many inverters you need to comply with the requirement, this is a very popular question nowadays, because the grid connection requirements are changing globally, I would say, and especially in Europe with the introduction of the RFG. So the DNOs and the TSOs, they're asking to generators to provide more support capabilities with their sites, mainly through reactive power, for example, in order to do some voltage support. The reactive power, it is very important to understand that the compliance is at the connection point, is not at the generation point. So, for example, you have here a curve of the inverter, a PQ capability curve of one of our inverters. However, in reality, this will not be like this. It will look more like you could see above, because this will take into considerations the contribution of your cables, of your transformers, of the distance to the connection point, and you need to make sure that your requirements are always below the operating point. In the G99 requirements, you need to be able to do this, for example, at 0.95 per unit voltage, and you also need to be able to provide a 0.95 power factor while operating at register capacity if the conditions are given. So you need to make sure that your capability curve is always above of these requirements, while taking into consideration at the same time the contribution of transformers, components like transformers and cables. This will define the number of inverters that you have on site. For example, if you want to do the contribution directly with the inverters, our inverters, they can work from 0.8 lagging to 0.8 leading power factor. So you can play with the number of inverters in order to comply with this requirement, and this is to be done with a dynamic simulation, like you can do a load flow study, and you will define if the amount of inverters that you have on site can allow you to comply with the reactive power requirements, and then you can be sure that your compliance or the DNO will be satisfied by the compliance of your site. This is one of the studies that you need to do, for example. This is everything I wanted to discuss today.